Welcome back, everybody, to the analysis seminar. Our speaker today is Carmelo Puliatti from the University of the Basque Country. And his title today is Blow-ups of Caloric Measure and Applications to Two-Phase Problems.
Okay, so thank you very much, Jose. Thank you for asking me to give this seminar, and thanks everybody for attending it. Okay, in this talk, I'm going to speak about something related with harmonic measure. Harmonic measure is an important object in mathematics. It was introduced more than a century ago, and it keeps being investigated in a broad variety of contexts. One of the reasons for the interest of this object in the mathematical community is that it provides a link between the analytic properties of a set and its geometry, in particular, the geometry of its boundary. So, in these talks, I'm going to present some results of a recent research of Mihalis Mourgoglou and myself. In this research, we studied something related to the equivalent for the heat equation of the harmonic measure, which is commonly referred to as caloric measure. So without any further excitation, let me first recall what harmonic measure is for the classical Laplacian in the classical Euclidean setting, say. So I will denote as Rn+1 my ambient space, and I will use the general notation, classical notation of omega for a domain, an open connected set here. The harmonic measure with pole at a point of the domain is a measure which lives on the boundary of the domain and which associates by this representation theorem to the integral of a continuous function on the boundary, the value of its harmonic extension to the domain evaluated at the pole P. Of course, as I said, this measure exists by raised representation theorem. And in particular, by assigning the value constant 1 to the function f, you can see that it is a probability measure by maximum principle, say. So here there is the picture that you will see in all the talks about harmonic measure. In particular, it was found in the 40s by Kakutani in 44 that harmonic measure has also a probabilistic counterpart and physical counterpart. Indeed, the harmonic measure of a subset of the boundary of omega can be interpreted as the heating probability of a Brownian motion which starts at P to first hit the boundary of omega at E. As I said, harmonic measure has been studied for more than 100 years before it was even called harmonic measure. In particular, one of the earliest results was a result of the Riss brothers in 1966, who proved that if we have a simply connected domain on the plane whose boundary is finite arc length, then harmonic measure is mutually absolutely continuous with respect to the arc length, which I denote here as Hausdorff measure restricted to the boundary of the domain. More recently, say 30 years ago, Bishop and Jones also in particular proved that this result can be localized in the boundary of a domain. And in particular, also the topology of the domain is itself very important in order to achieve this mutual absolute continuity. Indeed, they proved that this result fails without the presence of the simple connectedness assumption. At this point, it is very natural to ask oneself the question, so what is the connection between the mutual absolute continuity of surface measure, and the geometric properties of omega? This gave rise to a broad variety of research, which eventually culminated in a work by Azam, Hoffman, Martelli, Maiborova, Mourgoglou, Thorsen, Volberg of a few years ago, who proved the following. Consider a domain an open connected set in Rn+1, and take a subset of its boundary with with positive and finite Hausdorff measure. If we have mutual absolute continuity for harmonic measure and Hausdorff measure on E has a certain structure which is called rectifiability. What is a rectifiability? It's a very important concept in geometric measure theory, which is can be taught as a geometric measure theoretical equivalent of differential manifolds in differential geometry. And it is the following. A set is called rectifiable if up to a set of Hausdorff measure 0, it can be covered by a countable union of possibly rotated Lipschitz graphs. This concept, which I hereby define for sets, can be readily defined, also readily generalized for random measures. Their theorem that I showed before solved a question that was proposed by Bishop in the 90s. Christopher Bishop also proposed another question, which is a two-phase analog of the previous theorem. The question is the following. Consider two disjoint domains in Rn, omega1 and omega2. And consider 2 points, P1 and P2, in the respective domains, which will serve as poles. So that, in particular, each domain has its associated harmonic measure. What can we say for a portion of the common boundary if we know that the harmonic measure for omega1 is mutually absolutely continuous with respect to the harmonic measure for omega2? In particular, can we say that we have rectifiability in this portion of the common boundary? This problem was eventually solved in its full generality recently by Azamuroglu, Tolz, and Wolber after a series of researches. In particular, they show that if the two harmonic measures are mutually absolutely continuous on E, then we have rectifiability on a portion of E, which has full harmonic measure in E. Let me mention also that this result was first proven in plane by Bishop, so with other methods. This theorem involved a broad variety of techniques. For example, amongst these, there is also, let me mention, the deep connection of the race transform and uniform rectifiability, in particular the solution of the David-Ensem's problem and another work of Hirasarian and Tolz on quantitative rectifiability. But also another very, very important ingredient, which is one of the main ingredients, is a blow-up method at points of mutual absolute continuity. This method was first introduced in this context by Koenig, Price, and Toro in 2009, and further improved by Azamuroglu and Tolz more recently, under more strict topological assumptions on the boundary with respect to the theorem I previously showed. Okay, so Koenig, Price, and Toro, using the blow-up techniques at the points of mutual absolute continuity, proved, amongst other results, the following. If we have a domain in Rn+1, and we have that both the domain and its complement are so-called non-tangentially accessible, in the sense of Koenig and Jefferson and Koenig, for the people who know what this condition means. And we have mutual absolute continuity for the two respective harmonic measures, then the harmonic measures itself have Hausdorff dimension n, where Hausdorff dimension simply means that the measure is concentrated on a set of Hausdorff dimension n. In particular, the works of Koenig, Price, and Toro, and also the one of Azamuroglu and Tolz, heavily relied on blow-up techniques, in particular price theory of tangent measures. So by zooming in at these points to have a fine study of the boundary. Block techniques are present in a broad variety of contexts in mathematics, and the essence to define them is to have a set of dilations. So Azamuroglu and myself asked whether some similar result can hold in a parabolic context. And in particular, we wanted to examine the harmonic measure associated with the heat equation. Yeah, of course, let me mention that there's been activity in generalizing these results also for elliptic measure, but I'm not going to discuss them in the talk. So let me say what the harmonic measure is in the context of the heat equation. So I will use the notation x bar to denote points in the space-time Rn+1. So x will typically belong to the space part, and t will denote the time coordinate. And I will again denote by omega domains in the space-time. We want to consider domains whose section in time can vary, so they're non-cylindrical. So we want to try to be as much general as we can. So here I displayed the heat equation, which I'm sure all of you know. And heat equation has a fundamental solution, which can be written in terms of the Gaussian kernel and truncations for positive times. And Perron's method, in particular Wiener-Brillo's method, can be used to construct an equivalent of harmonic measure, which is caloric measure. But there is a significant difference here when we deal with general domains. Why? Because the continuous functions on the boundary are not resolutive for the heat equation. And one has to restrict the boundary to the so-called essential boundary of omega, which is a subset of the boundary. So before defining it, let me introduce some notation. I will denote as the parabolic norm the maximum of the Euclidean norm on Rn and 1/2 norm in the time variable. And I will use the notation CR for parabolic cylinders, which are centered at the point x bar and are given as the product of a Euclidean ball in Rn with radius r and have length r square, 2r square. So in particular, I will denote as CR plus the time forward cylinder, the upper part, say, and CR minus the time backward cylinder. So the essential boundary is given by the union, the disjoint union of two components. The so-called normal boundary, here denoted by dn, which is formed by the points of the boundary, whose backward cylinder is centered at the point, has non-empty intersection with the complement of the domain for every radius, with also the convention that we include the point at infinity in the case omega is unbounded. But this is not enough. We also to consider a slightly worse point from geometric point of view, and this is the so-called semi-singular boundary, which is formed by the set of points in the boundary of omega which do not belong to the normal boundary, such that the time forward cylinder meets the domain for all radius r greater than 0. Okay, I may realize that for people who've never seen this may look a little bit abstract, maybe, or not visual at the first impression. So I drew two pictures with two examples. First, let's consider the typical example of a cylinder. And it's not hard to realize that the essential boundary, which in this case coincides with the normal boundary, is formed by the union of the bottom part of the cylinder and the lateral part. This is consistent, for example, with the theory of the heat equation you may know on cylindrical domain, or is part also in some undergraduate courses, for example. I decided also to draw a slightly more involved domain to highlight some complexity that may arise. And I consider drew this domain omega, And I denoted, I indicated as in the black part, the essential boundary. So in particular, you see that it's given by the union of a normal part where the time backward cylinder meets the complement of the domain, and a spare point here where this doesn't happen, but it is this point belongs to a semi-singular part. In particular, one may realize that this singular part of the boundary essentially can happen if the domains stop at some point. So we have to rule out from the essential boundary the points for which there cannot be propagation of heat in the future. Another important concept in parabolic geometry is the one of heat walls, which are defined by means of the fundamental solution. A heat wall centered at a point x bar with radius rho is defined in this way that is displayed here by means of the fundamental solution. It's a different object with respect to a cylinder. In particular, I decided here to display the heat walls centered at 0, which is here, with radii respectively 1 and 2. You may see possibly curious characteristic at first that the heat wall itself do not contain the point x bar center and x bar, which is indeed lays on the boundary. Moreover, just to relate it with some Euclidean concept, one can see that the ball extends from minus rho to 0, and it is contained in a Euclidean ball, and the time projection is contained in a Euclidean ball of order square root of the radius. Of course, another peculiarity of the heat equation is that it is not adjoint as the Laplacian. In particular, it's also important to have in mind when dealing with heat equation to have in mind the adjoint heat equation, which I hereby display. And analogously to the heat equation, one can introduce the adjoint objects, such as the adjoint heat walls, adjoint essential boundary, just via time reflection. So another basic concept when in PDEs is the one of capacity. In particular, I'm interested in the heat capacity of a compact subset here, which is defined as the supremum of the measure of the set over the class of measures whose convolution with the fundamental solution is bounded by 1. The measure, of course, is non-negative, and it is supported inside of K. Why is this important? Why is capacity important? Of course, one of the reasons is that one can formulate boundary regularity criteria with respect to this capacity. In particular, there's a classical criteria, which by Lanconelli and Evans and Garepi, who prove that a point in the normal boundary is regular for the heat equation in the sense that the limit of the Perron-Wiener-Below solution converges to the boundary value, the value of the boundary of data, if and only if this integral diverges. In particular, we, Miales Morgoglu and myself, introduced a condition which we want to operate in, as quite general condition, which is related to this Wiener test. We say that a domain satisfies the time backwards capacity porosity condition if this capacity, well, the capacity at the level of a ball of radius r square, intersection the complement of the domain, can be bounded by the capacity of the ball in a sequence of small radii, in a suitable sequence of small radii that depend on the point psi. of course, in particular, you see that, yeah. Another, so let me first, before stating our main result, let me first introduce the notation for the non-homogeneous dilations in the parabolic space. Given 2 points, x bar and y bar in Rn+1, we denote by delta R the dilation, which is 1 homogeneous in space and 2 homogeneous in time, and by T y bar R bar, the blow up at the blow up map at y bar at level R, which is defined in this way in terms of dilation. We are essentially zooming in. And with this map in mind, we can define the blow up of measure as the push forward of the measure via this map. This is the analogous of what one does for tangent measures in the standard Euclidean space. And in particular, we can understand that a measure belongs to the parabolic set of tangent measure if it is non-zero and there exists a sequence of positive constants in radii which go to 0, such that we have the convergence of this integral to the integral of phi over the measure the nu for all test function phi in C infinity. So now is the moment for setting the main result of our investigation. Let us consider 2 domains, omega plus and omega minus, to be disjoint domains in Rn+1, disjoint time variable domains in Rn+1. And let Hn+1 with the pedix p denote the parabolic Hausdorff measure, which is nothing but this the measure which one can construct via the category construction as for the standard Hausdorff measure, but with parabolic cylinders replacing Euclidean balls. So what happens? What we showed is that if we have a subset of the intersection of the adjoint essential boundaries of omega plus and omega minus, with the following properties that the 2 domains have a joint time backwards capacity porosity condition along all the points of E, which says that we can find a sequence that works with the same radii for the 2 domains at the same time. And furthermore, we assume that omega plus and omega minus are regular both for the heat equation and the joint heat equation. And we have the last hypothesis, that which is the mutual absolute continuity on E for the 2 caloric measure. Then the 2 caloric measure on E have parabolic Hausdorff dimension n+1. Furthermore, that all the parabolic tangents measured at psi bar are of the form a constant times the parabolic Hausdorff measure restricted to a plane which contains a line parallel to the time axis. In the rest of the talk, I will also denote as calligraphic F this such set of measure, of flat measure. Okay, so first, before going on, just a quick disclaimer. This is just an almost correct version of the theorem, which involves some other conditions, but I don't want some other minor geometric condition, but I don't want to further discuss that. So just a few remarks before going to an idea of the proof. First, why can we use tangent measures and the tool, some important tools from geometric measure theory? Because it can be proved as it was done, for example, by Ito in a recent work, that a basic coverage covering theorem holds for parabolic balls. And in this way, we can use important geometric tools as the back differentiation theorem and some of the features of price theory of tangent measures, such as locality of tangent measures, or the tangent measure of tangent measure is a tangent measure, and other things. So, and what about the background hypothesis that we made? The time backwards capacity porosity condition is, which might seem a little bit abstract, maybe for people not in the field, maybe, is weaker than other typical assumptions that people make in this parabolic context, such as Reifenberg flatness, or parabolic non-tangential accessibility, or time backwards Alford-David regularity. So it makes sense to formulate this theorem under this generality. So, and also this research is motivated by other recent researches in the context of caloric measure and the heat equation on parabolic boundary value problems, singular integrals, the geometric studies, and the study of Lipschitz caloric capacity, for example. I don't have much time to discuss the whole history, but I just hereby include a list of people that contribute, say, in the last 20 years. So what time is it? Okay, let me just give an idea of the blow-up method that we use to prove this theorem and its main difficulties with respect to the harmonic measure case. So first, let's start with the setting. Consider that the measure omega plus and omega minus are mutually absolutely continuous on the subset of the boundary. In particular, there exists, by mutual absolute continuity, there exists the radon-Nikodym derivative, the omega plus or the omega minus, and we consider just, say, nice points in E, which are precisely the density points where the radon-Nikodym derivative is positive and finite, and which are Lebesgue points for H with respect to the omega plus. Of course, we can do this because by Lebesgue differentiation theorem, this set has full measure in E. Okay. In particular, for its point, one can prove that if we have a blow-up for omega plus, which converges weakly to a measure omega plus infinity, then the same blow-up with the same parameters, I mean, for omega minus converges to the same measure multiplied by the radon-Nikodym derivative evaluated at psi bar. So, furthermore, by price theory, or by an parabolic analog of price theorem, one can see that the space of tangent measures to omega plus at psi bar is non-empty for almost every point in gamma. So we can consider a measure omega plus infinity, which is arises as the limit of the blowups. So the proof of the main theorem is conducted in 3 separate steps. First, we have to study the geometry to understand the limit, the geometry of omega plus infinity. In particular, it's important, we want to realize it as the zero set of an adjoint caloric function on the whole space Rn plus 1. After doing so, we want to determine that this implies that there is a tangent measure which is flat and contains a line parallel to the time axis. Once this is achieved, we want to prove connectivity, to prove and invoke a connectivity result, which says that indeed all tangent measures are flat at xi bar. So I'm going to focus, as you may understand from the color, on the first step here, which is maybe the most delicate one in the parabolic setting. So Mialis and myself reduce the proof of the step one to the following main blow-up lemma. So let us assume that the domain omega is regular both for H and H star, and considering a pole P in omega. I'm gonna here just this lemma is just formulated for one domain, and we are gonna later apply to the two-phase problem. Okay, so and consider a sequence of radii which goes to 0. We denote by U the green function with pole at P bar, and by Uj the blow-ups of the green function with the same parameters as the blow-ups of the measure here. So I'm going to consider here. So the main lemma reads as follows. Assume that there exists a positive constant such that the capacity at the boundary of the domain satisfies the conditions of the time backwards capacity porosity, which is the one displayed here, and assume that the blow-ups converge weakly to a measure omega infinity. What we want to prove is that Uj converges in the L2 norm of a certain in a certain radius centered at 0 to a function U infinity. This function we further want to prove that is a joint caloric in the subset that you see displayed here. And one can also prove, we want also a bound for its L2 norm for some proper dilation of the cylinder. In terms of the caloric measure at infinity for a proper dilation of the cylinder. Furthermore, we want to identify omega infinity as the caloric measure associated with U infinity, which is by this formula here. So how this proof goes? This proof, an analogous lemma was proved by Azamurkoglu, and Volberg in the harmonic measure setting. So the first temptation is, of course, to try to reproduce the proof. So one see that by some considerations, some lemmas that I'm not going to discuss here, that one can bound from below the harmonic measure at a cylinder centered at psi bar via the supremum in the cylinder and domain of the green function multiplied by rj to the n for some proper m greater than 1. So we're scaling it for we have that the lim sup of Uj of the blow up, see, which is of course positive by can be bounded by the omega infinity measure of the closure of Cm. In particular, this says that Uj, the sequence Uj for j big enough is uniformly bounded on a possibly smaller cylinder. So the point is, of course, we have this uniformly bounded sequence. Does it admit a convergent subsequent in a proper space, or in particular in L2? So what are the most known compactness results for in this segment? For example, we may wonder, as it was done in Zamorgolo and Tolsa, to argue by equicontinuity. But this is not possible under our regularity condition, because equicontinuity results involve Hölder continuity at the boundary, which cannot be proved under our hypothesis. The result which is used in Adamov-Goldklosser and Wahlberg is the Rayleigh-Kondratyev theorem, compactness theorem for Sobolev spaces on cylinders. So let's see. Consider U to be the extension by zero of the green function outside the domain for sufficient small radii which lead outside the pole. And in particular, one has that U is a joint subcaloric in the boundary cylinder. Hence, one can apply Kachople inequality on the space part for the space gradient. And this inequality reads as follows here. So we can rescale it. And we have Kachople inequality for the blowups of Uj. The big problem, however, is how to deal with the time part and the time derivative. Indeed, the function U fails to be a joint caloric in the whole cylinder centered at the boundary, which makes the things hard. And in order to obviate this problem, which at first Miles and myself were a little bit desperate about this, we surprisingly had to use optimal transfer theory. So let me introduce it. Let D denote domain in Rn, and nu and md be the set of finite sign measures on D. Now, let's consider the Kantorovich-Rubinstein norm on M, which is defined as the supremum of the integral over mu of the functions phi in this Lipschitz class, which is defined as the set of Lipschitz functions on the closure of D, whose norm is bounded by 1, and that vanish on the boundary of D. Here, there's this type, just the type. So, using the modified one Wasserstein distance with between functions with possibly different masses, one can identify the Banach dual of M with the Kantorovich-Rubinstein norm. In particular, there's a linear bijection between Lipschitz 0,1 function on the bar and phi hat here functions here defined. In particular, in order to prove this result, one has to follow the scheme of a proof of Edwards in 2011, which and using the basic theory of an appropriate variant, which as one has to check carefully, of the basic theory of one Wasserstein distance. In particular, Kantorovich duality, and this duality formula here that is displayed here, and this approach. However, at this point, we may think that we are fine, but this space here is not complete in general. So one has to identify, in order for our method to work, one has to make it complete. So let M tilde denote its completion, or say closure inside Lip 0,1, and denote as TU the first order distribution associated via U, like this. What one can prove is that it's possible to identify the completion of M tilde as in the space of distribution as a set of distribution as a set distribution represented by the divergence of a L1 DRN function. And furthermore, we also have this equality of norms once we quotient L1 with respect to the divergence-free function. Okay. This proof goes by we argue, in order to achieve this, we argue by a paper of Bouchité, Champion, and Jimenez, and Bouchité, Boutas, and Di Pascal for almost 20 years ago. And we had to check carefully that all this proof translates also to our context. So once we have this, we introduced a novel parabolic Sobolev space, which is defined on the domain times a timing interval I via this norm that we see displayed here. That is to say, the L2 norm on this cylinder, plus the normal space gradient, and the integral of the Kantorovich-Rubinstein norm of the time derivative. So after all this discussion, we have that this is a Banach space. And what we did afterward is to observe that by a work of Jacques Simon from the 80s, this parabolic Sobolev space embeds compactly in L2 of D times I. And this was fundamental for us. So once we had this, we were actually able to prove a novel boundary Cacciopoli type inequality for the square of the green function here, as you see, in terms of the Kantorovich-Rubinstein norm. So that when rescaling it, we finally had our bound for the norm of the power of the green function. In this way, we could prove that there exists a sequence Bj which converges to B infinity, to a function B infinity, in the L2 space of the unit parabolic cylinder. So by almost routine arguments and functional analytic arguments, we could achieve the convergence of a subsequence of Uj as in L2. Okay. So this is all I wanted to say for concerning our main lemma. So let me quickly point out that, in particular, let's go back now to the two-phase problem and let's see how to apply it, more or less, just an idea about how to apply it. Consider the blowups omega j of omega plus converging weakly to omega plus infinity, and the blowups of omega j minus converging to h times omega plus infinity, as I explained before. So using our main lemma and other arguments, one can prove that this composition of the green function converges to U infinity in L2 of a proper cylinder with a proper radius given by the blow-up lemma. Furthermore, a very important point for us was that U infinity extends to a joint caloric function on Rn+1. Why is this very important for us? Because this allowed us, for example, to use unique continuation results, which in general do not hold for caloric or joint caloric functions which are not globally defined, or hold in other fashions, which were not enough for us. Okay. In particular, having this unique continuation results, we could identify the support of the tangent measure omega plus infinity with the nodal set of U infinity, or equivalent with the boundary of the non-zero part of U plus and U minus. And we know that by the set via sigma, for example. What we had to do at this point was to understand the geometry of this nodal set. In particular, something which is crucial to us also is also that we could write the measure omega plus infinity as the surface measure, which is defined as lattice, as you see here, times the normal, the negative inner normal derivative on a tight slice of U infinity. So we identified the Poisson kernel of omega plus infinity. And so at this point, what we had to do is to understand the geometry of this nodal set. In particular, the way we did this is we split the nodal set in a time regular part and a space regular part and a totally singular part. And we proved that the time regular and space and the fully singular part are of zero measure. So it remains on a full measure a part of the nodal set, where this set can be represented as locally as the graph of a function in the right coordinates, which contain a line parallel time to the time axis. And this explains why the class of tangent measures which arises from this blow-up lemma are precisely the flat measure which contain which are vertical, say. In the last minutes of the talk, which I'm gonna finish soon, I'm not gonna focus on further technicalities on the proof, but I'm just going to present other results which can be proved by our blow-up method. One result is a caloric analog of a famous theorem of Theorem, which was more recently proved via analytic arguments by Tolsa and Volcker. The proof is the following. The theorem is the following. Consider three disjoint open sets in Rn+1, which are regular both for H and H star. And these three sets have their associated caloric measures. If these three measures are respectively mutually absolutely continuous on a portion of the common boundary, then we can prove that the three caloric measures are zero. I mean, here there's zero. Also, what I also proved, which I'm not going to discuss, and I'm going to finish the talk. I'm going to mention it for people who know this. This terminology is that if we have parabolic delta Reffenberg flat domain and the logarithm of the Radon-Nikodym derivative belongs to a parabolic version of BMO, then what we can prove by our method is that this domain is in particular vanishing Reffenberg flat. And this was a result which was first obtained by Koenig and Toro in the harmonic measure case. And it was in the same year proved by Nystrom for caloric measure. So we reobtained Nystrom results by this way. Also, in particular, our method is applicable to this setting because these Reffenberg flat domains satisfy stronger assumption than the one we assume in our theorem. And this is all I wanted to say today. So thank you for your attention.
Thank you very much for the talk, Carmelo. Are there questions for our speaker? I have one at least. So the regularity in your main theorem, the condition, the geometric condition on the boundary, you say it's more general, less restrictive than other that have been considered in the caloric setting.
Yes.
Right?
Yes.
I have two questions about that. Second, first, is it formally weaker, or do you know examples of domains which satisfy one but do not satisfy the other? So do you know TB-PCP domains which fail to satisfy the formally stronger conditions that you cite on the next slide?
Well, I don't have the example ready for you, but yeah, in general, for example, capacity density conditions amount to ask this condition for all the radii at the boundary. Okay. So in this sense, this is weaker. For example, also, as I said, it's weaker than alpha-studied regularity, for example, a 10 backwards assumption on alpha-studied regularity. So honestly, I don't have examples ready, but I'm sorry.
Okay, and this TB-PCP in the caloric setting would correspond to what condition on the elliptic setting, which I'm more used to?
Well, we call that capacity porosity. Following a literature also in the elliptic setting, there are typical assumptions. It's typical also in the elliptic literature to assume this kind of conditions to have in the context of regularity to the boundary. So our notation is not completely new. So essentially, it's a thickness notation for a thickness condition for the x0 of the boundary. So,
okay.
For x0 of the domain. Sorry.
Okay.
It's called the capacity density condition typically.
So yeah. It generalizes that, and
it's a capacity density condition.
But I think but there's also in the literature, we found it somewhere, I don't remember the precise reference, the term porosity for in this context. So typically it's more used as Professor Martel said, this capacity density condition, but there's some reference also for capacity
actually
porosity.
I was curious about the word porosity because
thank you, Professor Martel.
Well, may I say something?
Sure.
Like the capacity porosity that we use is just like you find one sequence that this holds. Like the capacity density is like a uniform estimate. So that's why it gives like Helder continuity. And this, you should not expect like the capacity porosity to give Helder continuity.
Yeah.
And that's like the hard thing.
Okay, and that's what porosity means, right?
Yeah.
That there are gaps between the radii which you can,
Exactly. And also like the problem here, like where did you have to assume this condition was because like in the Euclidean case, like in my paper with Jonas, Xavi, and Sasha, there was we could actually show that like there exist two sequences, actually one sequence that works for both domains. I mean, the interior and the exterior, let's say, domains, that they have like simultaneously big complement, and also in the Lebesgue measure. But here, because of the situation like of the parabolic situation, is like everything is not like about balls, so cylinders in this particular case, but backward cylinders. So essentially, you instead like of having a dichotomy argument like the Euclidean case, now here you have like 4 cases, and you cannot really, argue as in the Euclidean case, because you have like you have like backwards, forward, and then interior, exterior. So you have like 4 different domains. So essentially, like, I mean, we couldn't, I don't know, we tried a lot, but we couldn't prove the original results. So that's why we had to do this.
I'm sorry I didn't mention it because I wanted to mention it, but since it's my first parabolic talk, in the flow I forgot. I'm sorry, but thank you for pointing it out, Mialis.
No worries.
We thank Carmelo again. Thank you very much for the talk.
Thank you for inviting me and everybody for attending the talk.